All right, so let's look at an example of these stress strain calculations. All right, so we go to another quiz question. So I have the gummy load versus extension curve below, along with some initial measurements that I took. And what I want you to do is calculate the engineering stress and strain at this point here, mentioned on the load extension graph. So looking at this point on the load extension plot, along with the initial measurements, calculate the engineering stress and strain. So do that, make those calculations, answer that in the quiz, and come back and we will look at these calculations more thoroughly. All right, so let's go ahead and take a look at this, and let's start with stress. So we know that stress is force over area. And so we have the force from the plot. So this is 0.6, this is 0.8, so 0.7, 0.75. And so that's in kilogram force. This is kind of an interesting unit. I'm not sure exactly why they use it, but it's basically mass. And so you still have to multiply it by the gravitational constant. So the force is 0.75 kilogram force multiplied by the acceleration due to gravity, so 9.81 meters per second. That will get you newtons. And then the area, if we go back, so this was a rectangular cross section based on the width and the thickness. And so that will have a rectangular cross section. So we multiply the thickness and the width here, and I'm doing so in meters so that it comes out to be pascals. So this is newtons because we're using kilogram and meter squared, and then this is meters squared down here. So if we calculate that, we'll get 134,360 pascals. And like I said, often stress is quite high in terms of pascals, and so we use something like kilopascals for this. So 134.4 kilopascals would be more useful than what we just looked at. Okay, so that was engineering stress. Excuse me. So now let's look at strain, engineering strain, which is epsilon down here. So that was defined as the change in length over the initial length. And again, change in length is another name for elongation. So going back to the plot, we see that at that point, we have an extension or elongation of 225, because it's right in the middle there, millimeters. So that's the top portion. And then the initial length was given here as 36.91. So putting those two in, we get a value of 6.1 elongation, or 6.1 strain, engineering strain. And again, you can use this as the unitless, or you could put millimeters over millimeters. So that is the value of stress and strain at that point. Right? Well, we have, so I just did this as an example, just this one point. But as you can imagine, we have computers, right? This load extension data was plotted on a computer. We have all the load values and all the extension values. So we can easily just apply these same calculations to all of the data that you see here and convert it to engineering stress, engineering strain. And so you see the shape, it's the same. But it has units now that are stress and strain. So this is where now, if we test the properties of a gummy tensile dog bone of one size and compare it to the other, as long as we use these normalized units of stress and strain, the curves should look the same, right? This won't be any different than a larger dog bone. Whereas this one will be altered based on the size of the specimen. So we're doing this to enable us to compare mechanical properties across different sample sizes, because that's what we're after, right? You don't build a skyscraper with I-beam of the exact same size as a material in another skyscraper, right? So we need to know the general properties before we can look at the specific properties of a particular product.